Welcome to a special Halloween edition of Mythology. Recently I did a video on Fermat's mega famous last theorem. Fermat's theorem says that the pretty Pythagorean integer identities like 3 squared plus 4 squared equals 5 squared or 5 squared plus 12 squared equals 13 squared don't have non-triple counterparts if the exponent 2 is replaced by any integer greater than 2. Today I'd like to tell you about a second theorem associated with the great Pierre de Fermat. It goes by the name of Fermat's little theorem and is also about powers of integers. Very important, at least for people obsessed with movie maths like me and Marty, both of Fermat's theorems have featured in The Simpsons and Futurama. In 1995, just around the time the proof of Fermat's last theorem was announced, Homer stumbles across a pretend counterexample to Fermat's last theorem. A really fun maths troll by the Simpsons writers that had millions of viewers reach for their calculators. Then, in the 2014 Simpsons Futurama crossover episode, the equation at the core of Fermat's little theorem is discovered by my alter ego, Professor Frink. There, in the upper left corner of the hatch in Bender's head. Some of you may not be familiar with the three-stroke equal sign and the mod thing in brackets. I'll explain later, but luckily we can also express Fermat's little theorem in simpler terms like this here. The vertical green line means divides into or is a factor of. So what this says is that if you pick any prime number and any positive integer a, then the prime must divide the difference on the right. For a really simple example, let's choose our prime to be 3 and the integer to be 4. Fermat's little theorem then tells us that 3 divides 4 cubed minus 4. Of course, that's easy to check directly, since 3 divides 64 minus 4, which is equal to 60. But without doing the arithmetic, and just by looking at the expression on the right, it's not at all obvious why this should be true, right? How can we be sure Fermat's little theorem is always true, no matter what monster-sized prime and integer we've chosen? And why should we care, right? Of course, mathematicians care simply because that's the way we're built. And in a minute, I'll show you a really beautiful proof of Fermat's little theorem. But just in case that's not sufficient incentive, though it really should be, I also promise to show you 2 really cool applications of Fermat's little theorem. Our first application is an unexpected and really weird way to hunt down prime numbers, something which is very important for things like credit card encryption schemes. Along the way, we'll also encounter some of my favorite numbers, the mysterious Fermat pseudoprimes. As a second application, I'll turn Fermat's little theorem into a tool that you can use to solve really frightening Halloween problems, like this one here. Oh, and we'll also have some more Futurama. But first the proof. It turns out that to prove Fermat's little theorem, all we have to do is to count some pretty necklaces. What do necklaces have to do with any of this? Don't worry, of course I'll explain. As regular viewers are probably now very used to, I'll focus on one example which is sufficiently generic to illustrate the general proof. So let's again choose the integer to be 4 and let's prove that the prime 7 divides 4 to the power of 7 minus 4 in a way that will also clearly work for any prime and any positive integer. Now, what we're going to do is to count the number of necklaces of length 7, where each of the 7 beads can be one of 4 colors. Except, not all of the beads can be the same color. Here's an example. And here's another one. So it's okay to not use all the colors. The only thing we avoid is choosing all the beads to be of one color. So that's not allowed, okay? Again, 7 beads, 4 colors, not all the same, okay? Also important, we consider rotated versions of a necklace to count as one and the same necklace, okay? So all of these guys here, they're all the same necklace. However, we consider 2 necklaces that are mirror images to be different as long as they cannot be rotated to coincide, okay? We'll show that the total number of such necklaces is 4 to the power of 7 minus 4 divided by 7. Now, of course, the number of different necklaces must be an integer, right? But for that to be the case, 7 must divide 4 to the power of 7 minus 4, which is what we want to prove. Sneaky, huh? Okay, time to begin counting necklaces. To do this, we first cut each necklace and straighten it out like this. Okay, straight and straight. But of course, there are other ways to cut the necklace, giving rise to different strings. For example, cutting here gives this string here. There are 7 gaps between the beads, and so there are 7 possible strings that we can cut. And these 7 cuts correspond to the following 7, and this is really, really important, 7 different strings of beads. Now, if we had started with all possible necklaces and imagine cutting each of them in all possible ways, then we'd obviously end up with all possible strings. And the total number of strings is very easy to count. Each string has 7 beads, and each bead can have any of 4 colors. So the total number of different strings is 4 times 4 times 4, 7 times, which comes to 4 to the power of 7 strings. Now, remember, we didn't begin with absolutely all necklaces. We left out the boring one-color ones, which also means we miss out on the boring one-color strings. There are how many of those? Well, 4 colors, so there's 4 of those, right? And so our total number of strings is 4 to the power of 7 minus 4. Almost there. Now, every necklace under consideration also gives rise to 7 different strings, as in our example. And that means that the number of necklaces we began with is the number down there divided by 7. Ta-da! That's it. How sneaky and how absolutely ingenious was that? Yes, but something's a little bit weird here, right? You think you've got it? Yes. What's peculiar is that at no point did I use the fact that 7 is a prime number. So where can our proof go wrong if we don't use a prime number? Well, the problem is that if we replace our prime number 7 with a composite number, then not all strings that we get by cutting a necklace are necessarily different. And obtaining 7 different strings for each necklace was absolutely critical for our counting argument. For example, if we use 9 beads instead of 7 beads, one possible necklace looks like this. In this necklace, things repeat every 3 beats, which means that when we cut this necklace in all possible ways, we only get 3 different strings rather than 9. And this invalidates the last step in our proof. I'll leave it as a first challenge for you to show in the comments that this sort of periodic necklace cannot occur if a necklace has a prime number of beads and at least 2 colors. Oh, and just in case you're wondering, 9 doesn't divide 4 to the power of 9 minus 4. But wait a minute. We're actually on to something extra interesting here, which means it's time for another t-shirt. Ta-da! Now, as I was saying, 9 not dividing 4 to the power of 9 minus 4 is also interesting and leads to our first application of Fermat's little theorem. Fermat's little theorem tells us that if 9 was prime, then 9 would divide 4 to the power of 9 minus 4. But we know that actually 9 does not divide 4 to the power of 9 minus 4. So 9 cannot be a prime. I know. Wow.
Oh my God.
Incredible. Stop the presses, right? However, what this suggests is that we can investigate whether or not some mystery number m is prime by swapping m for 9 and checking for divisibility. And if the difference on the right is not divisible by m, then m is definitely not prime. On the other hand, what if the difference on the right is divisible by m? Does this guarantee that m is prime? Sadly, the answer is no. For example, if we test m equals 4, then the difference is definitely divisible by 4, since both terms on the right are divisible by 4. But of course, 4 is very much not prime. Bummer! Still, 4 is a pretty special number for this setup, so maybe this is all worth a little more exploration. So let's do an experiment. We let Mathematica check divisibility for the first 1000 integers. Let's see how many non-primes and maybe primes get discovered this way, okay? However, before firing up the machine, I'll make an adjustment. Those powers here will get very big very fast. There's also nothing special about using 4 in Fermat's little theorem, and we could use any integer greater than 1. So let's start at the start and keep those powers as small as possible by replacing 4 with 2. Now we'll let Mathematica do its thing. That's the output of my program, and as you can see at the beginning, it's spot on. All the non-primes, 4, 6, 8, etc. fail our divisibility test. And so Fermat's little theorem proves they are non-primes. In fact, it's only when we get to 341 that we have a non-prime that our test thinks may be prime. And there's only 3 such numbers under 1000. But we don't have to put up with nonsense from those 3 troublemakers. 2 was just one possible choice for our integers, so let's throw 3 at them. And that works. Using 3 identifies 341 and 645 as non-prime numbers. One annoying number to go. So we can throw 4 at 561. And if that doesn't work, then 5, and then 6 and 7, and so on. Something's got to work, right? Wrong. It turns out that 561 is infinitely annoying. None of our Fermat's little theorem tests will show that 561 is composite. Numbers like 561, which Fermat's little theorem cannot distinguish from primes, are called Fermat pseudoprimes, or Carmichael numbers, named after the American mathematician Robert Daniel Carmichael. Actually, they were misnamed since Carmichael was neither the first to discover these numbers nor the first to seriously investigate them. So maybe we should call them pseudo-Carmichael numbers. It appears that the real discoverer of these numbers was the Czech mathematician Václav Šimerka. Anyway, Carmichael numbers are very rare. Among the first billion positive integers, there are over 50 million primes, but only 646 Carmichael numbers. Still, it was proved in 1994 that overall there are infinitely many Carmichael numbers. Really tricky stuff, actually. Knowing about these numbers and the fact that they are relatively rare is also of practical importance. Being able to easily generate very large primes, primes that have 1000 plus binary digits, is of key importance for all sorts of encryption algorithms, such as the algorithms that keep your credit card transactions safe. Well, keeps them safe until some company stuffs things up, right? And despite the crazy powers that appear in Fermat's little theorem, and despite the existence of those infinitely annoying pseudoprimes, primality tests based on Fermat's little theorem turn out to be more useful than pretty much anything else, making Fermat's little theorem of huge practical importance. Now, before moving on to our second Fermat's little theorem application, let me just mention a characterization of these mysterious pseudoprimes. This really beautiful characterization was discovered, well before Carmichael of course, by the German mathematician Alwin Reinhold Korselt. At first glance, proving that a number like 561 is a pseudoprime looks insanely difficult because it involves showing that 561 divides the difference on the right for all infinitely many choices of the integer a. However, Korselt proved that if you know the prime factorization of a number, then you can pretty much tell at a glance whether the number is a Carmichael number. Just subtract 1 from every one of the numbers inside. Okay. Then our number is a Carmichael number if and only if all the numbers on the left are different, and if they all divide the number on the right. So a number is a Carmichael number if none of its prime factors repeat, and if all its prime factors minus 1 divide the number minus 1. Pretty amazing characterization, isn't it? I love it. Okay, an arithmetic challenge for you. use Korsel's characterization to prove that 1729 is a Carmichael number?
No calculators.
Marty has something with calculators. And now a quick pop culture maths puzzle. Why do you think the Futurama writers kept sneaking the number 1729 into the program? Is it because it is a pseudoprime? And while we're here, why are my initials BP on the Futurama spaceship Nimbus? Now for our second Fermat little theorem application, and time for yet another t-shirt. Ta-da! Okay, finally, to get into the Halloween spirit, let me show you how you can figure out by hand what the remainder is when you divide the seriously monstrous number 11 to the power of 666 by the unlucky prime 13. For this, we need to recast Fermat's little theorem into the form that appears in Bender's head. What do? Well, we first take the common factor a out of the difference, like that. This shows that if the prime p does not divide the first factor, our integer a, then it must divide the second factor, right? Pretty obvious. Okay, now to our unlucky prime 13 and the base 11 of our monster integer. Of course, 13 does not divide 11, and so Fermat's little theorem promises us that 13 divides 11 to the power of 12 minus 1. In other words, when you divide 11 to the power of 12 by 13, you get a remainder of what? Well, 1 of course. In maths lingo, we write that succinctly like this. Okay, and what we are interested in is the value of the pumpkin in this equation. We can sneak up on the pumpkin by starting with our tiny 11 to the power of 12. Now comes the trick. Since 11 to the power of 12 has remainder 1 when divided by 13, so does any power of 11 to the power of 12. We leave that for you as an easy challenge. On the left, we can pull the n into the brackets. Now we've almost revealed our pumpkin. 12 times 55 is 660. So if we choose n equals 55, then we get this. Okay? Almost there. The power is still 6 short of our 666. But you can check by hand that 11 to the power of 6 has remainder 12 on division by unlucky 13. Finally, we multiply the left sides together and the right sides together to arrive at our final answer, a remainder of 1 times 12 is equal to 12. Can you justify the last step of this calculation? Okay, last challenge for you. What is the remainder of the super unlucky evil 666 to the power of 666 when you divide it by 13? I should warn you that if you don't succeed in submitting the correct answer in the comments by midnight on Halloween, Jason will pay you a visit. And don't try to be smart, only one answer, otherwise I'll tell Jason. And don't use a calculator, otherwise I'll tell Marty. And that's it for today. Happy Halloween.